Okay guys, as stated in the trailer and in the welcome video, we start with several case studies. The first section is chemical processes. Main idea is to start using Aspen Plus, getting to know what is the minimum requirements, the physical property environment, the simulation environment, flow sheeting, and so on, getting results, etc. Then we get a little bit more technical and start with the process analysis, which are three. Then we get a little bit more on rigorous unit operations, such as the heat exchanger and RadFrac. Then we do one case study on plant economy and another one in dynamic control. Okay, so let me explain you a little bit more so you get the idea of what we're going to be covering. So this is what we're going to be doing in case study number 1. The main outcome is to get this simulation. As you can see, we're going to be working extensively. We're going to be learning how to open a new file, how to save, set up the physical property environment, binary parameters, flow sheeting, adding unit operations, streams, etc. All this is going to be seen before each case study. So this is just an overview, so you get the idea of what is inside this case study. But of course, when we get to the case study, we're going to review this so you get the idea of what exactly is what you're going to do. As stated before, running the simulation and viewing results. Case study number 2, distillation unit, which is distill and DSTW, then some pumps and so on. We are going to see also how to get help on Aspen Plus. Physical property environment, we're going to be using the analysis tools, which is very common for distillations in order to see what are the TXY diagrams and PXY diagrams as well. Case study number 3, pretty straightforward, compression, a heater, then a mixer from a recycle. So this is new. We're going to be adding a recycling and purging streams. A reactor, CSTR, continuous stirred tank reactor, valving, chiller. Then we got this membrane. Also, what's here? The RadFrac. We're going to be presenting the RadFrac as well. We continue with case study number 4, still analyzing a little bit on flow sheeting techniques, adding reactions to a PFR, which is actually a plug flow reactor, a pipe reactor, heat exchanger, a little bit more on the heat X, shortcut, tube and shell exchanger, and plotting some results on the units. As you can see, still we have some recycling and purging. The second part will be process analysis, which is 5, 6, and 7, design specification, optimization, and sensitivity analysis, respectively. Case study number 5 is a little bit more, let's say, long, or let's say a lot of unit operations. You can see I show you how to add more representative figures. This is, for instance, comes from plant X. This goes to the distillation unit. You state the recycle going back, timestamp, and some, let's say this will be the reactor part and this will be the separation scheme and so on. Actually, there's also the design specification. Very important to ensure that we use design specification. Then we go to case study number 6. The main idea is to optimize using constraints. So optimize is going to maybe maximize the earnings while considering maybe that this cooler has a maximum heat duty which cannot be achieved or overused and so on. We then present the Gibbs reactor. Case study number 7, we get to see manipulators, which actually is the double. What it will do this, will separate the stream into 2, duplicate it, and we're going to try to see which reactor is convenient for our reaction kinetics. So I don't want to be a little bit spoiler here, but we work with the plug flow reactor because it's the best one. And then we continue with the separation scheme and membrane, recycling, and so on. We use equilibrium reactions and, of course, the sensitivity analysis. Then we continue with rigorous units. We start with the rigorous heat exchanger, shell and tube exchanger, comparing what's rating, design, and simulation. RadFrac, which is used for equilibrium stage operations. either binary or multiple compositions. We start to analyze pressure profiles, temperature profiles, mole flow rates, and the difference between trays, packings, and more on how to size the equipment, tray spacing, and so on. Then we continue with the same rat track unit, but we work with distillation. Remember, distillation is essentially separation of a distillate and a bottom. We have plenty of stages. We want to use the sensitivity analysis to verify what will be the best or optimal feed stage. Maybe you want to try the heat duty of the reboiler, the most convenient one, or the feed to distillate rate ratio, and so on. Now we continue with the last part right here, which is case study 11 and 12. In case study number 11, we're going to be talking about the ammonia economics, how to set up the utilities of the plant right here. For instance, this is going to be fueled or with liquefied petroleum gases. This will be water cool. You were using heating system, maybe you will be for instance, saying steam, high pressure, medium pressure, or low pressure. This part right here and this part right here is electricity operated. This has a cooling jacket, which is electricity operated. Then you can add the stream cost, the raw material cost, product cost. Maybe you want to add a price on purge. Maybe you need to pay to burn that purge, or maybe you can sell it to another plant or as another product. That's up to you. You can also add prices or cost to the materials inside here. Okay, the main idea is to optimize profits, and the main idea first will be to see if it is actually feasible to do a plant on this, and then of course optimize for profits. And we are going to do two case scenarios, maybe the USA comparison versus the European Union prices. We're going to set up some typical prices and see which one is better. Finally, but not least, because actually this is a huge topic, which is plant dynamics and control. What we're going to do here is to convert our simple simulation. As you can see, we have these valves right here, just to ensure that this is a pressure-driven simulation. If you know a little bit on dynamics, you will see that this will be controlled by opening and closing the valves. We are going to export to a Aspen dynamic file, and we're going to be using a Aspen dynamic software, which technically is another software, but it's considered from Aspen Plus. So if you have Aspen Plus, it's okay, you should have that. We're going to learn how to fill up the dynamic folders and then to start our simulation. We're going to add some controllers. We're going to see how to graph the response versus the point value, the set point, and so on, and then we're going to tune those controllers. What we want to do as engineers is that if this feed increases drastically, we can control that in this part right here, or maybe you want to see if you change a temperature here, it drops, you gotta then tell the reboiler to increase its duty in order to to counterbalance that temperature. Eventually what you want to see is this is time and this is your temperature set point. If it drops, what you want to do is, let's say this is the heat duty. When you see these drops, you are going to increase heat duty according to your tuning, and what you want to see is that eventually this goes as it was before. Okay guys, so these are the 12 case study. Hopefully you like them, and if you have any doubt regarding the content, just let me know and I will let you know and explain you what are the requirements, what do you need, what do we see, and so on. See you in the next lecture.